because we are already late by 3 minutes. All right, so then let me welcome you once again. Yes, and what we do today, as we have talked in the past couple of times, we try to understand the so-called superstring theory, and today we try to go into more details, possibly step by step. Okay, and so as I said that the basic motivation for, just to recap in few lines, the basic motivation to go into supersymmetry and superstrings is the following. In nature, the nature is very well described by the so-called standard model. A standard model has bosons and fermions both, right? You have 6 quarks, 6 leptons, they are all fermions. And you have gauge bosons, they are bosons. So you see, bosonic theory, bosonic string theory cannot describe the fermions. And without including fermions into our theory would not be nowhere near a complete theory. So we do need to do it. Now there are two different approaches. One is called as the RNS superstring formalism, Raymond Nebu-Schwarz formalism, and the other one is called as Green-Schwarz formalism. Green-Schwarz formalism we will take up in details next Friday. Okay, and today we will take up in details the the RNS superstring formalism. What is the difference in these two? We need to know very clearly. In the RNS approach, we have a supersymmetric theory on the word sheet. In the other approach, Green-Schwarz formalism, we have supersymmetry on the space-time manifold, which is 10-dimensional. Word sheet is 2-dimensional. Okay, so we have the supersymmetry on the word sheet. How do we do it? We introduce additional fields into our theory, which are fermions. And obviously, if you have fermions and you have bosons both in your theory, you need some symmetry that would relate the bosons and the fermions. In our language of field theory or string field theory, bosons and fermions would mean bosonic fields and fermionic fields. Okay, so there has to be a symmetry which relates bosonic fields into fermionic fields and fermionic fields to the bosonic fields. And this is the supersymmetry does that job for us. So supersymmetry relates boson fields and fermionic fields. And this was understood for the first time in 1971 by Gervais and Sakita. They explicitly derived the supersymmetry transformations and showed that the theory is invariant under this supersymmetry transformations. And here in this one, the boson fields and fermion fields, they get related to each other. Okay, and this is what we want. So that does our job. Okay, so in the spectrum, when we discuss the mass spectrum of this theory, we will realize that yes, indeed, in our theory, in the mass spectrum, we do have both kinds of particles, bosons as well as fermions. In our earlier approach that we did last summer, That was purely bosonic string theory, and the mass spectrum only had bosons. There were no fermions in the mass spectrum. Well, one more additional thing that we used to have in the bosonic string theory, that was the tachyonic states. Tachyonic states are the states with the negative mass operator or the negative mass square. So these tachyonic states would are unrealistic states, okay, and because nothing can move faster than the universal velocity or universal speed, the speed of light, as one says. And so, and moreover, the tachyonic states also imply that the quantum vacuum is unstable. So one would like to get rid of the tachyonic states. Now in this superstring theory approach, we will see explicitly how one can avoid tachyonic states. They do appear in the mass spectrum in the first place when we do the theory in the usual manner. However, at the end, you make use of the so-called GSO projection. These are three names, Gliozzi, Serge, and Oli. These three gentlemen. So one redefines the some operators, and with the help of that, you can get rid of the tachyonic state. They are automatically eliminated from the mass spectrum. Okay, so this we will do in the next lecture. Okay, today let us see how far we can go, and then I mean, we will go exactly the way we have. First, we will try to understand the basics of this superstring theory in this RNS formalism, and then we will go into the so-called equations of motion and the boundary terms and the boundary conditions, and we will have the Fourier modes and eventually the mass spectrum of the theory in different sectors. Okay, good. So now what we do in this approach, we introduce Fermi fields denoted by psi mu of sigma alpha. You see, in the bosonic string theory, we had already the string coordinates or the string fields were x mu. They were bosonic, and these are fermions. Okay. They are fermions. Okay. So sigma alpha we know is sigma 0, sigma 1. This could be taken as tau and sigma. You could also take sigma alpha as sigma plus, sigma minus, where you can define the plus minus sigma, and accordingly your derivatives would change. So they would be del plus minus are your del tau plus minus del sigma. Okay, so with the help of these two, one can always go back and forth from the instant form to the light form, and from light form to the instant form. Okay, wherever we like, we keep in mind. And now you see, these fields x mu and whatever the corresponding Fourier modes, if we Fourier expand this x mu, all those quantities would obey Bose-Einstein statistics. However, for psi mu by themselves, as well as if you make their Fourier expansion, the Fourier modes, they would all obey Fermi-Dirac statistics, okay, which are characterized by anti-commutation relations. These bosonic variables are characterized by commutation relations, and Fermi variables are characterized by anti-commutation relations. Okay, so